Hello, my name is Abhishek Bansal. In this video, I am going to talk on magnetostatics. So the magnets is not something we started in the Renaissance period. We know that these phenomenons, besides the rubbing on the carpets, sparks producing, the lodestones, the mariner compass, these were even known before this Renaissance. Rather, it traces back to the ancient times. So I am going to, because the other thing is that we can in the magnetostatics, let's start with we know that the magnitude of the flux density can be defined by the mechanical torque, and that's exerted on the magnetic dipole. So it's equal to mu into B. Here B is what? The magnetic flux density only, and mu is the magnetic. This is mu, not u. Mu is the magnetic moment of the dipole. So this magnetic field flux density is also sometimes called the magnetic induction. And let's start with the current. Okay, so a current that corresponds to the changes in to the a current it corresponds to the charges in motion. So we define the current density by J, that's measured in units of positive charge crossing unit area per unit time. Okay, so if this current density is confined to the wires of small cross section, we usually integrate over the small cross sectional area and speak of a current of that. Okay, so many amount of current like 2 amperes flowing or 1 ampere is flowing. In this now there is also a conservation of charge which comes into play. This is not my I have some different kind of postulates and propositions. I am talking on the existing, not established by me. So the conservation of charge, it demands that the charge density at any point in space, it is related to the current density in that neighborhood by the continuity equation. So we are having the partial derivative with respect to t of the rho plus the divergence of the current density. This is known as the continuity equation, and this expresses the physical fact that a decrease in the charge increase inside the small volume with time, it must correspond to a flow of charge out through the surface of the small volume, because the total amount of charge has to be conserved. Therefore, inside the small volume with the time, it must correspond with the flow of charge that is outside through the surface of the small volume. So the steady state phenomena, if we are going to talk on the steady state phenomena, so it's going to be characterized by no change in the net charge density. Okay, that means we are basically dealing with the magnetostatics that says the divergence is the 0. So if I just remove the time derivative of that rho, this is basically we are going to do this is known as the magnetostatics. Okay, so we know that the magnetostatics then starts with the Biot and the Savart law, and it was said that the wires that's carrying the electric currents, they produce the deflections of permanent magnetic dipoles that were placed in the neighborhood. So the currents were the sources of the magnetic flux density. Biot and Savart, and then we have an Ampere also. So they related the magnetic induction B to the currents. Okay, so it started with that we have a DL, that is an element of length that's pointing in the direction of the current flow of a filamentary wire. It carries a current I and x is a coordinate vector from the element of length to an observation point P. So then the elemental flux density dB at point P is given by dB is equal to Ki dl into x by x cube. So if you want to see, this is basically an inverse square law, like we have studied the Coulomb's law, that also following the inverse square law. We have seen the x cube there also, and here we have the vector character, because here it's going to be given by the magnitude and the direction. Okay, so this is basically not equivalent to the electric field, and it is, this also fact is not established by me. This is what is mentioned in the textbooks and taught, that this equation is not the magnetic equivalent of the electric field of a point charge, and we cannot identify I dot dl as q. Though I mentioned that this is basically an analog like an inverse square law. So it means that if suppose I am going to have an element induction dB, what it means that if we are having this dl here, small here, and we are going to have this is an element of length we are taking. From the element of length we are just taking dl. It's pointing in the direction of, this element of length is also pointing in the direction of what? Current flow. That means this is here following, and this is here I, and this is a dl. So this element of length, it is carrying a current I, and we are taking an x coordinate vector from an element of length to an observation point P. So suppose this P is the observation point, then the vector would be defined in this way. X, this would there, this is the P, and this is the direction of the magnetic flux density or the magnetic flux induction. Okay, so we have just said that this magnetic field is not an analogous, or it's not basically an equivalent. It's not, rather the correct word should be equivalent. It's not an equivalent of an electric field, because here one element only as one element of a sum over a continuous set, then the sum representing the magnetic induction of the current loop or a circuit. So basically this is talking about this, that this is basically this is meaning as only as one element of a sum of a continuous over that. So the continuity equation that we have just mentioned, the continuity equation here, the divergence of the is equal to 0, current density is 0. So this continuity equation now satisfied for this element dl, or the current element is IDL, okay, alone. The current comes nowhere and disappears, and after traversing the length dl. Okay, so we have to realize that the current is actually charge in motion to replace IDL by QV, where Q is the charge and V is the velocity. So the flux density for such a charge in motion would be then what? B would be what? K. Now we are reducing it by QV, so this would be Q, and V into X by X cube. Okay, so this expression is basically time dependent, and furthermore it would be valid only for charges whose velocities are slow compared to that of the light. So here we are not taking the velocity of this charge equal or equivalent to the velocity of the light. We are specially mentioned that it would be valid only for charges whose velocities are small, that are small compared to that of the light. and whose accelerations can be neglected. Okay. So we can linearly superpose the basic magnetic flux elements by integration to determine the magnetic flux density due to various configurations of the current carrying wires. So if suppose we have a long straight wire, it's carrying a current I, and we can say now instead of this, now I am taking a long wire, or now let's take a long wire. Here we have the DL element. It is in the direction of the current flowing. The I is flowing in the direction downward. So we have mentioned that this is a P position point. Okay, and this is an H here. We want to draw perpendicular. It would be, let's do this P is here. Perpendicular. Let's say the distance is R. Let's say this angle is theta. Then the magnetic field would be in this magnetic induction. Similarly, we can draw the magnetic induction here also because the current is still flowing, and we can say that a current I can be seen to be directed along the line, along the normal to the plane containing the wire and the observation point. So the lines of magnetic induction, they are concentric circles around the wire. So B is equal to, the magnitude B is equal to mu naught by 4 pi IR minus infinity to infinity dl by r square plus l square 3 by 2, and if we are going to solve this, we are going to get mu naught by 2 pi IR. So R is the distance from the observation point to the wire. So this is called as the first experimental result found by the Byers and Savard. Okay. Here the magnitude of induction, that is a B, it varies in the same way as electric field due to a long line of uniform linear charge density. So here it says due to this it forms some analogy between the electrostatic and the magnetostatic problems. But here one must remember this is a vector characterization of the field would be different. Now Ampere laws, the Ampere experiment did not deal directly with the determination of the relation between the currents and the magnetic induction, but they were concerned with the force that one current carrying wire experiences in the presence of another. So we already know that a current element produces a magnetic induction. So we phrase that the force law as the force experienced by the current I dl in the presence of the magnetic induction. Okay, so the Ampere was talking in terms of force. So the force would be dF. The dF is equal to I1 dl1 into B. So if the external field B is due to the closed current loop with I2, then the total force which a closed loop current with current I is going to experience what? Is going to experience F is equal to F from 1 to 2, because here we are taking what, in the Ampere case we are taking what the force one current carrying wire experiences in the presence of another current carrying wire. So force that's going to be experienced is the F12 mu naught by 4 pi I1 I2 over the double integral of the dl1 into dl2 into x12 by into x12 divided by modulus of this x12 cube. Okay, so the line, we have taken the line integrals around 2 loops. Okay, and x12 is basically what? It is the vector distance from line element dl2 to dl1. So this was the mathematical statement of the Ampere's observation about forces between the current carrying loops. So if we manipulate the integrand, we can put it in a form that is symmetric to the dl1 and dl2. Okay. So if we are going to manipulate it in the symmetric form, let's put it in a symmetric form, because that's going to be explicitly satisfying the Newton's third law. So what I am going to get, dl1 into dl2 into x12 divided by modulus of x12 the whole cube, and this is equal to the negative of dl1 dot dl2 into x12 divided by the modulus of x12 the whole cube plus dl2 dl1 dot x12 by x12 cube. Okay, so here you have to see that this second term that I have written here, it's not I have derived it, this is all given in the textbook only. So this second term, it involves a differential and the integral over the dl1. So it's not going to give any contribution to the integral if we are going to say the paths are closed and extended to infinity. To which integral I am talking about? The double integral, closed integral that I have just talked on, about the closed double integral which was closed in the earlier. Okay, because this was, I have placed the mu naught upon 4 pi, and this is basically the force on 1 on 2. Okay. So this is in the Ampere's law. Okay, the Ampere's law would then become this thing only. Here, instead of, you put a dot product between these two, and this would be x12 only, and that shows the thing. So that shows the symmetry in the integration. Because this term is not going to contribute to the integral, as we have taken the path closed or even extended to the infinity. So each of the two long parallel straight wires which were distance d apart, they carry currents I1 and I2, and the experience is a force per unit length, that is taking a differential df by dl, and is going to be directed perpendicularly towards the other wire, and it is going to be of the magnitude mu naught by 2 pi I1 I2 by d. So the force is going to be attractive or repulsive. It's going to be attractive if the currents flow in the same direction. If the currents flow in the opposite direction, the force is going to be repulsive. But there the force is going to exist between the two current carrying wires, and we can use it to define the magnetic flux density in that way, that is independent of the permanent magnetic dipoles. So if a current density, let's say we have the current density Jx, it is in external magnetic flux density Bx, then the elemental force law implies that the total force on the current distribution would be what? The total current distribution would be Jx into Bx d cube x. And similarly, if we are going to say the total torque, that's going to equal to integral of x into j into b, j cross b d cube x. Okay. So let's write the flux density equation, or rather we should write the basic law for the magnetic induction, which will be defined by basically this equation: dB is equal to Ki dl into x by x cube. Let's write this equation in terms of the current density. Once we are writing the equation in terms of current density, it becomes B of an x equal to mu naught bound 4 pi integral of j of the x prime into x minus x prime by x minus x prime cube dq x bar.